Hello students, my name is Samir Sabarwal and I teach in KRM DAV College, Nakodar. I teach chemistry. First of all, I am grateful to our worthy principal Dr. Anup Words, who has given us a chance to interact with the students of our college through this channel. I'm going to teach heterocyclic compounds, which is a topic of BSc non-medical semester 4. This is basically a complete topic. I want to share one thing that I'm quite hopeful that students of not only the students of our college but the students of the rest of the college of this region are also able to get benefit from this channel. So let me start my topic. My topic is heterocyclic compounds. Students, hetero means different cyclic compounds. So basically we divide these compounds into two categories. One is non-aromatic or alicyclic heterocyclic compounds, and the second one is aromatic heterocyclic compounds. So first of all, we must know what do we mean by aromatic compounds. Aromatic compounds are those compounds which follow Huckel rule, and this is already we have got knowledge about aromatic compounds in our previous classes, that those compounds which follow Huckel rule, that is 4n plus 2 pi electron rule, 4n plus 2 pi electron rule. So n is a number that may be 0, 1, 2, 3. So the basic point is aromatic compounds are those compounds which follow Huckel rule. There is complete delocalization of pi electrons, and third one, the molecule must be planar one. So we can understand the topic only if we know what are aromatic compounds. So aromatic compounds, I gave you simple example of aromatic compound, that is benzene, and we know a lot about benzene or their derivatives. This is a molecule which is having 6 pi electron cloud. If you put n is equal to 1, right, 4 plus 2 will come out to be 6. So there are 6 pi electrons. So benzene is aromatic. This is planar, complete delocalization of pi electrons, and this is following Huckel rule. So those compounds which are following these rules, they are coming under aromatic compounds. Now, if I take non-aromatic compounds, means they are not following Huckel rule, they are not aromatic one. Let me take examples of non-aromatic heterocyclic. Hetero means when we have atom other than carbon in the ring. Just like we may have oxygen, nitrogen or sulfur in the ring. So this is an example of first molecule. This is oxyrane. We also call this as ethylene oxide, right? Oxyrane. Next one is oxetane. This is a 4-membered ring. There is one oxygen atom in the ring, so we call this as an oxetane. They are basically known by their common names. Then we have tetrahydrofuran. See students, this is tetrahydrofuran where one oxygen is there, and next one is tetrahydropyran. This is basically tetrahydropyran, yeah, oxygen, but this is a 6-membered ring. Exactly, next one is 1,4-dioxygen. I repeat, 1,4-dioxane having 2 oxygen in the ring. Aziridine, right? This is a 3-membered ring where the nitrogen is central atom. We have so many examples, but I want to take only those examples which are related to our subject. Like piperidine, this is again a very special molecule. Now, in our syllabus of heterocyclic compounds, I will teach you aromatic heterocyclic compounds. The first one is pyrrole. See, pyrrole. This is a 5-membered ring with the nitrogen atom as an heteroatom. Then we have furan. Earlier we did tetrahydrofuran. So that is why I was emphasizing on this tetrahydrofuran. If you remove 4 hydrogens from here and you put 2 double bonds, we get furan. So this is a very special molecule and this is part of our syllabus. Then thiophene, if you replace oxygen with sulfur, we get thiophene. So there are 3 5-membered heterocyclic aromatic compounds which are in syllabus, and we will study their methods of preparation, their physical properties and chemical properties. And the next part of our syllabus is 6-membered heterocyclic compounds, that is pyridine. It's a very famous molecule. We use pyridine in so many reactions. Pyridine is used as a solvent and there is one lone pair, so it behaves as a basic molecule. Exactly, we may have pyrazole. See the difference. In pyrrole there is 1 nitrogen, but in pyrazole there are 2 nitrogen atoms. Exactly, we have imidazole. There are 2 nitrogen atoms in the 5-membered ring, but you can differentiate them with their positions. Exactly, we may have benzofuran, as the name signifies. The furan group is attached to the benzene ring, so we call this a benzofuran. Quinoline, again a very special molecule, quinoline and isoquinoline. If you recall this, that we use isoquinoline in Lindlar's catalyst, which is palladium barium carbonate or barium sulfate poisoned with sulfur, boiling xylene or quinoline. We use these molecules in Lindlar's catalyst. This is a purine, which is a nitrogenous base, which is a part of our genetic material, right? DNA or RNA. So let me sum up the thing. We are going to study heterocyclic aromatic compounds. Earlier we did aromatic compounds and we took the reference of benzene to explain aromatic compound. Benzene and derivative of benzene were taught in the previous classes. Now here, since this is a higher class, here we are going to teach you aromaticity through heterocyclic compounds. So if we consider our syllabus, we have basically 4 molecules. One is pyrrole, second is furan, third is thiophene, and fourth one is pyridine. Now let me tell you, subject is not difficult. If we know the basics, we are able to write everything. We are able to express each and everything. Now if I start from benzene, question comes, which reaction is the most favorable reaction of benzene? We know that benzene is aromatic compound, and aromatic compounds behave like saturated molecules, and there is some extra stability of the molecule because of resonance. So basically aromatic compounds are those which are stabilized by resonance energy. Is that clear? So first of all, if you are unable to understand the resonance energy, go through previous classes. First of all, get the meaning of resonance energy. So resonance energy is the energy which comes through resonance. Now, benzene is an aromatic compound. It behaves like a saturated molecule like alkanes. And which kind of reaction is the most favorable reaction of alkanes? We must know the most favorable reaction of alkanes is free radical substitution reaction. So I give stress to word substitution. Why substitution? Because alkanes are saturated molecule. And if you take benzene, benzene is not a saturated molecule. Benzene is an unsaturated molecule. Even though unsaturation is there, but it shows substitution reaction. Students, we are quite aware that addition reaction is the characteristic feature of unsaturated compounds. So I want to explain it here that though benzene is unsaturated, but it behaves like a saturated molecule because of resonance. And because of resonance, addition reaction is not favorable in benzene. Then question comes, which kind of substitution is favorable in benzene? Answer is very clear. Obviously, this is substitution, and benzene is electron-rich molecule because of pi cloud. So pi cloud is available, electron-rich molecule. Benzene is electron-rich molecule. So which kind of reagent will attack benzene? Obviously, that reagent which has attraction for electron. So I'm talking about electrophiles. The most important characteristic reaction of benzene is electrophilic substitution reaction. So whenever we consider syllabus of organic chemistry where aromatic compounds come, you may take +1, +2, BSc 1, 2, 3. We teach aromaticity through benzene or heterocyclic compounds, and we want to convey one thing, that the favorable reaction of aromatic compounds is electrophilic substitution. Since electrophilic substitution reaction is favorable in benzene, it is damn clear that this substitution is again a characteristic feature of heterocyclic aromatic compounds. Why? Because we are talking about aromatic compounds, and electrophilic substitution is a characteristic feature of aromatic compounds. Now, first of all, I want to compare benzene with the molecules of this syllabus, because I'm going to teach you 4 molecules: pyrrole, furan, thiophene, and pyridine. First of all, I'm going to compare 3 molecules: pyrrole, furan, and thiophene with benzene. Students, if you remember that the resonance energy in case of benzene, for benzene, resonance energy is around 150 kilojoule per mole. Is that correct? And resonance energy in case of pyrrole, furan, and thiophene, it is written over here. Let me compare on the decreasing order, on the basis of decreasing order. You see, first of all comes benzene, having maximum resonance energy. Then comes thiophene, 125 kilojoule per mole. Pyrrole, 92 kilojoule per mole. And furan, 72 kilojoule per mole. So, students, just try to analyze that which molecule is the most stable out of these 4 molecules. Answer is clear, that is benzene, because its resonance energy is maximum. Then comes thiophene, where resonance energy is 125 kilojoule. Resonance is more prevalent in thiophene. Then comes pyrrole, where resonance energy is 92 kilojoule per mole. And then furan, where resonance energy is 72 kilojoule per mole. It means benzene is the most stable one. Okay, and if benzene is showing electrophilic substitution reaction, then definitely rest of the molecules will also show electrophilic substitution reaction. Then Students, question comes, out of these molecules, which molecule is showing a maximum electrophilic substitution reaction? Now, thing is clear that electrophilic substitution is the characteristic feature of these molecules. The question arises, if we do comparison, which molecule is going to show maximum electrophilic substitution reaction? So when we think like this, then we will be able to understand the subject properly. Let me answer this. If I take Pyro, I'm going to start with Pyro, and I simply want to say that the most favorable reaction is electrophilic substitution, and out of these four molecules, electrophilic substitution is more prevalent in Pyro. How come this? There are 5 atoms in the ring, whereas in benzene we have 6 atoms. So we get 6 pi electron from one benzene molecule, and we get 6 electron from 5 atoms in the ring, and nitrogen has one lone pair. How come 6 electrons are there? You should know this. You just consider 2 electrons of heteroatom, 2 pi electrons here and 2 pi here. So how many electrons are there? 2, 2, 2, 6. So exactly benzene is having 6 electrons and 6 electrons of pi cloud, and this pyrrole is also having 6 electrons of pi cloud. It means as compared to benzene, more electron density is available in pyrrole. Not only this, if we compare 4 molecules, in these 3 molecules we have, you can say these are 5-membered ring, and all of 3 types are contributing 6 electrons. So 6 electrons are shared, are coming from 5 atoms, 1, 2, 3, 4, 5. And whereas in this case, 6 electrons are coming from 6 atoms. It means in which case electron density is more? Yeah, definitely in these cases electron density is more. So definitely electrophilic substitution reaction is going to be more favorable in pyrrole, furan and thiophene as compared to benzene, and this reaction is most favorable in which case? Pyrrole. So electrophilic substitution is really highly favorable in pyrrole, and I will answer that question properly. Now if I consider the resonance of pyrrole, this is the structure of pyrrole. We did these topics in lower classes too. You can see I'm showing delocalization. The lone pair comes here and pi cloud will come to this carbon. When I shift this electron pair here, this nitrogen will acquire a positive charge. In the next step, because we are going for delocalization, this electron pair will come to this point and shifting of pi electrons, right? Now you can see the third structure. Don't forget to put positive sign on the nitrogen, because nitrogen has donated its lone pair. Electron pair comes here, right? And shifting of pi cloud. So see that positive charge on nitrogen is retaining. So you can feel that pyrrole is showing 5 resonating structures, right? Now students, you are also able to draw the resonating structures of furan. You do one thing, you simply replace nitrogen with oxygen. Is that clear? If you replace nitrogen with oxygen, see, you have got resonating structures of furan. Similarly, you can draw resonating structures of thiophene too, with one difference. that in thiophene, empty d orbital is there. It means I am able to get more number of resonating structures in thiophene because of the availability of empty d orbital in thiophene. But in pyrrole and furan, nitrogen and oxygen belonging to the second period, no d orbital is there. So we will get only 5 resonating structures in case of pyrrole and furan, but we will get more than 5 resonating structures in case of thiophene because of the participation of sulfur. So I hope so you are able to draw the resonating structures of pyrrole, furan and thiophene. And students, we must know the rules of resonance. You will get my answer easily of my previous question. You can answer that question. If I compare the resonating structures, right? Let us take case of pyrrole and furan. What do you think? In which case resonating structures are more stable? Or which molecule is going to give more resonance stabilization? Pyrrole or furan? Though I have mentioned the values, in case of pyrrole, this is 92 and furan, this is 72. So answer is given, but point comes how? Okay students, if we compare the resonating structures, in case of pyrrole, we have nitrogen, and in case of furan, we have oxygen. Now nitrogen being less electronegative than oxygen, okay, is more capable of donating lone pairs. Though positive charge is not stable on electronegative elements, even then, if you compare the resonating structures of pyrrole and furan, nitrogen is possessing positive charge in the resonating structure, and in furan, oxygen is possessing positive charge on 4 structures. See, this one, second, third, fourth, and fifth. Now, in which case positive charge is more stable, on oxygen or nitrogen? Very clear. Positive charge is relatively more stable on nitrogen because nitrogen is less electronegative. So this is the basic rule of resonance. One basic point is, if that structure is stable where positive charge is lying on less electronegative element and negative charge is lying on more electronegative element. It means positive charge on electronegative element is less stable. So if you have to compare 2 structures in which 2 different atoms are present and both are possessing positive charges, those heteroatoms are possessing positive charges, in which both structures are unstable. But out of these 2 structures, which is more relatively unstable? Obviously, that structure where electronegativity of atom is more. This is what I want to convey. Then if I take pyrrole and furan, nitrogen is possessing positive charge in its resonating structure. In furan, oxygen is possessing positive charge in its resonating structure. But nitrogen, the structures of nitrogen are more stable because positive charge is relatively more stable on less electronegative. So that is why the contribution of resonance is more in pyrrole as compared to furan. And you see that in case of thiophene, how much is the resonance energy? 125. Why is it so? Obviously because the number of resonating structures in thiophene is much more than the resonating structures in case of pyrrole and furan. So thing is very clear. If you want to understand, we normally get this question in our final exam. Draw the structure of pyrrole or furan or thiophene. Let us start with this. You know the structure of benzene? Benzene is a planar molecule where each carbon atom is showing sp2 hybridization. So how come this is planar? This is benzene. Here each carbon atom is sp2 hybridized. So you can answer this well. This is the ground state configuration of carbon. 2s, 2p. Fine. In order to make 4 bonds, we want 4 half-filled orbitals. Excite one electron from 2s orbital. So this is excited state of carbon. This is 2s and 2p. Now see, for each carbon there are 3 sigma bonds and 1 pi bond. It means we must know that sigma bonds are formed from hybridized orbitals. It means 1s and 2p orbitals will intermix to give us 3 hybridized orbitals. That is why it is sp2 hybridization. So this is unhybridized orbital. Now it means you are able to justify the rest of the carbons. If I take Pyro C, this is the structure of Pyro. What about nitrogen? Ground state configuration. This is ground state configuration. Then how do we justify the structure of Pyro? What we feel that there is an excitation of electron from 2s to 2p. There is no 2d in nitrogen because it is belonging to second period. So I get this situation. Now what do you say? There are 3 sigma bonds, and sigma bonds are obtained from hybridized orbitals. So this is going to show sp2 hybridization. Is that clear? And this is an unhybridized orbital. Unhybridized. Is that clear? So this is an unhybridized orbital, and that is why we have 6 pi electrons for pyrrole, because those electrons which are delocalized, they always come from unhybridized orbital. Now you are quite able to understand the structure of pyrrole by taking a reference of benzene. Here each carbon is showing sp2 hybridization. There is one unhybridized orbital, and of each carbon, so that is why we are able to get 6 unhybridized orbitals of carbon. Those orbitals will overlap to give us pi cloud above and below the plane. And if I simply do one thing, if I remove one carbon atom and replace carbon atom with nitrogen and make it a 5-membered ring, is that clear? What is going to happen? This is nitrogen. I have replaced carbon with nitrogen. This is the configuration of nitrogen. In order to justify the structure, I shift electron to higher orbital, showing sp2 hybridization, and very clear that this lone pair of nitrogen is belonging to unhybridized orbital, and that is why this lone pair is not available for donation. Now you can easily answer that pyrrole is less basic molecule. I want to compare pyrrole with, see which molecule? Pyridine. Let me simplify this. what is the difference between pyrrole and pyridine? Pyrrole is heterocyclic compound, which is 5-membered compound with the nitrogen as an heteroatom, and in pyridine this is a 6-membered heterocyclic aromatic compound with nitrogen as an heteroatom. So the difference is it's a 5-membered and pyridine is a 6-membered. Now students, we know that pyridine is an aromatic compound. So if you count for the 6 pi electrons, because aromatic is a characteristic feature of aromatic compound. So this is 6 pi electrons. It means this lone pair of nitrogen is not participating in hybridization. Sorry, let me clarify this. That these are 6 pi electrons and this lone pair of electrons is not participating in the pi cloud. It means this lone pair is coming from hybridized orbital. So in pyridine, nitrogen shows, see how many hybridized orbitals are there? 1, 2 and 3. So this is showing sp2 hybridization. Is that clear to you? See the structure of pyridine, that lone pair of nitrogen is not participating in the pi cloud. It is hybridized orbital. As you can count the number of electrons of nitrogen. 2 from this bond, 2 from this 4, 2 from this 6 and 2 8. So nitrogen can accommodate at the most 8 electrons. So if you please sum up the whole thing, topic is heterocyclic compounds. We have non-aromatic heterocyclic. We have aromatic heterocyclic. In this chapter, I'm going to teach you heterocyclic aromatic compounds. So the 4 molecules which we are going to study are pyrrole, furan, thiophene and pyridine. Since they are aromatic, criteria for aromaticity is Huckel's rule, delocalization and planar, right? And the characteristic reaction of aromatic compounds is electrophilic substitution, as we know it well in case of benzene. It means these molecules are also going to show electrophilic substitution reaction. It's a characteristic feature. So and try to compare them on the basis of resonance, in which case resonance is the most favorable, that is benzene, then thiophene, then pyrrole, then furan. Just try to compare them properly. Why is it so? Why resonance is more favorable in benzene? You will come to know the answers in my next lecture. Fine. Then electrophilic substitution is the most favorable.